From time to time, I get questions about thermal bridging. What is it? How does it affect our buildings? How do we manage it? And as spray foam professionals, how do we explain it to prospects and customers in the market?
Hi, I'm Robert Niney, your spray foam advisor and the guy in the Hawaiian shirt. I wear the Hawaiian shirt as a symbol of freedom and flexibility, something that all business owners should want to achieve. You know how most SPF contractors start their business because of their technical skills, but they have no plan for growth? There's no consistency because decisions in their business are made on the fly. They are just trying to get through the day. And they are spread too thin because they do everything themselves. Well, what I do is help SPF contractors like that measure profitability, identify the key activities that drive success in their business, and create a game plan that develops consistency and growth. Let's get into it.
So let's talk about that today. What is thermal bridging? Well, you should be familiar with thermal performance, R value, and how energy or heat transfers through building materials. That's what R value is. It's a measurement of the resistance to heat flow. Thermal bridging describes the phenomena that occurs when you have dissimilar materials with different thermal rates of transfer or different R values near each other. And when you have different materials with different R values next to each other in the same assembly, then the rate that the heat transfers through one of those materials can be much faster in some cases than the material right next to it. For example, let's consider the most common case of thermal bridging that we deal with. This occurs when we have steel studs or metal studs and we insulate the cavity between the metal studs. The metal transfers heat much faster than the insulation inside the cavity, and the result of this is the overall thermal performance of the wall assembly is significantly lower than the cavity R value because the thermal transfer through the metal studs is so high that it degrades the thermal performance of the overall wall system. For example, if we put an R20 inside a metal stud cavity, the thermal performance of the metal studs is so bad that the overall wall assembly is going to perform closer to an R13. So there's going to be a significant degradation in the performance compared to the installed R value. Now, this is not exact. There are some equations that can be used to determine the exact overall performance or to approximate the exact overall performance. So don't quote me on this exact figure. I'm just trying to illustrate the situation using this example. So, how do we overcome thermal bridging? The most common answer is continuous insulation. Continuous insulation overcomes thermal bridging by creating a thermal break and not allowing any structural members with lower thermal performance like metal studs or even wood studs to transfer heat and energy directly through the building envelope. The building code has started moving in this direction with guidelines for continuous insulation. For example, on the exterior of a commercial building built with metal studs or built with a steel frame and CMUs inside the steel frame, a big way for spray foam to help the thermal efficiency of this building is by providing a continuous insulation on the exterior of this assembly. This method mitigates the thermal bridging. It helps reduce the heat transfer through the structural members so the building doesn't have thermal bridging occurring. Another good example of thermal bridging can be seen in roof decks. Now, it is not really a failure point, so it is often less noticeable, but if you look at the exterior of a roof where the roof deck has been insulated between the rafters, after a thin layer of snow you can occasionally see melted lines every 16 to 24 inches on center where the rafters have allowed enough heat to pass through the roof and melt the snow above the rafters much faster than the snow above the foam insulating roof cavity. The best way to address thermal bridging is to reduce the opportunity for low R value materials to have direct contact from the inside to the outside of the building envelope assembly. This is the purpose behind continuous insulation. In the roof assembly example that I mentioned, where you might see melted snow or evaporated dew lines, you can identify roof rafter lines from the exterior in that situation. The key to solving this problem is to insulate over the face of the rafters on the inside of the attic providing a form of continuous insulation and reducing the heat loss through the rafters. I'm glad I could share some thoughts and ideas about thermal bridging with you today. Take this information out into the market, share it with your customers, and go out and get more business. Like this video and make sure to subscribe here on YouTube so you are notified when we release future videos. And if a strategy discussion might be helpful for you and your business, you can book a call with me at spfbiz.com.